Welcome to this lecture on geomorphic change detection. Specifically, we're going to be answering the question, why should river managers monitor topographic change and calculate sediment budgets? Rivers on Earth have a variety of different three-dimensional shapes. In this slide, we can see some satellite images of just some of the forms of rivers that are found in the Philippines. As river managers, we need to understand the processes that control a specific river type that we might find in a particular area, and we might also want to understand the dynamism, or how that river is changing through time. Clearly, process rates will be different depending upon the different factors that control sediment flux or sediment input to a reach, and how quickly that material is transported through a river reach. The multi-thread channel that you can see here in the bottom left-hand side of this diagram is clearly going to have quite different process rates to a meandering channel with gravel bars that we can see in the top-hand right of this slide. Understanding and quantifying sediment transport rates and topographic change for different types of systems is a subject and an open question for scientific study, but also it can be an applied management question to understand rates of change and what's causing those changes. Many of the rivers on Earth are not natural any longer. Human impacts have changed the space that rivers have to migrate across their floodplains, and they've also changed the input of sediment from upstreaming. So, for example, impoundments for hydroelectricity and water supply might change flow hydrographs and limit the transport of sediment downstream. The clearance of vegetation might supply more finer sediments from erosion of land to a particular river reach. And interventions along a river reach itself, such as lateral confinement to create bridging points, might also influence a river's capacity to naturally convey sediment downstream. Sediment budgets can contribute to understanding some of the impacts of some of this anthropogenic activity and can help to inform appropriate management interventions to mitigate some of those consequences, both in terms of risk, for example, to erosion and flood, but also to maximise the ecology of a river in terms of retaining its natural ecological functions. Lane's balance is a conceptual model in fluvial geomorphology that can help indicate whether a reach is likely to degrade or lower its elevation, or aggrade, i.e. increase its elevation, as a consequence of changing sediment or water supply from upstream. We have a balance overall. If we change the flux of sediment or the flux of water through a river reach, that might cause either degradation or aggradation. If we increase water, then we're likely to cause our balance to move towards a degrading state. The additional water, perhaps due to increased storminess associated with climate change, gives the river more capacity to transport sediment and therefore results in the river eroding into its bed. If we increase the flux of sediment, perhaps from a landslide event upstream that causes more sediment to be entrained and conveyed through our reach of interest, that might cause the riverbed to aggrade, so the bed of the river to increase in elevation. A river response, however, isn't necessarily quite as simple as just causing change to the elevation of the riverbed. A stream might also adjust by varying its sediment size, so becoming coarser or finer in response to these perturbations of changes in water or discharge, and also the slope might vary by becoming flatter or steeper, for example by changing the sinuosity of meander bends in response to changes in discharge. So to understand a river's long-term behaviour, we might need to monitor it over annual, decadal or century timescales, depending upon the rates of channel morphodynamics. But we also might be interested in much shorter term changes in a river's topography and explaining why those changes occur. Sediment budgeting is essentially a great big jigsaw puzzle. What we want to do is we want to understand all the different inputs and outputs of sediment within a particular area of interest. So this diagram by Frings et al., published in 2017, does just this. It illustrates sediment sources, such as from upstream, from tributaries, from secondary channels, from input, for example, by artificial nourishment schemes where sediment is injected to supplement sediment within a river, perhaps as a restoration management intervention to a river that had become coarse through time, through the connectivity between a river's sediment sources being cut off, perhaps due to flood embankments or interventions upstream. Other inputs might be from the downstream area in an estuarine system or from diffuse sediment sources such as bank erosion. This model also identifies some of the sediment outputs, a flux to the downstream area, to secondary channels, sediment that's lost due to anthropogenic activities such as dredging, sediment that's trapped in groin fields, that's deposited on the floodplain, or the output of finer sediment fractions through abrasion of the sediment fraction of interest. If inputs are equal to outputs, there'll be no morphological change. If, however, there's an imbalance between inputs and outputs, we'll expect the bed level of the total reach to vary, either by increasing or decreasing. And it's often these changes in bed level that we're interested in from a river management perspective, because aggradation, for example, can cause the performance of flood defences to decrease because we're filling up our river channel with material and it's unable to convey the flux of discharge that those defences were designed for. And conversely, degradation might erode the foundations of flood defences or bridge piers, which might cause sediment-related hazards. So Frings went on to make 10 arguments for calculating sediment budgets: to create order in the apparent chaos of data, to identify morphological problems, to find smart solutions to problems, to set research agendas and monitoring strategies, to optimise dredging and nourishment strategies, to coordinate river management on a basin scale, to assess the consequence of human interventions, to improve numerical models, to explain river management to society, and train future generations of river managers. And in the next few slides, I'm going to focus on a few of these, particularly those that I've been involved in my recent research. Frings published a paper in 2019 on the River Rhine in Germany, and long-time sediment monitoring had generated an apparent paradox. Echo soundings, measurements of the river's bathymetry, suggested there was bed degradation, but gravel bedload transport measurements downstream indicated that was decreasing transport downstream. So what was going on? Was gravel eroding overall? Scientists monitored different grain size fractions, gravel, sand and silt, throughout the reach of interest. They derived a sediment budget to identify the different pathways of each of these fractions, and they found that sand was being eroded, but then it's being transported downstream in suspension. So the original monitoring design of only measuring gravel bedload transport downstream actually wasn't capturing that sand fraction, which therefore was resulting in an imbalanced sediment budget. So by asking some questions here about the different fractions of sediment that are in motion and may change within a river reach, the scientists were able to answer the conundrum of what fractions were causing channel change and where those fractions were being transported to. We're going to the Wye River in New Zealand next to discuss about a river management problem that is leading to very real morphological challenges in river management. The Wairau River in New Zealand, there was a flood event on March the 25th and 26th, 2019. Just over 1 metre of rainfall fell in 48 hours. The discharge of the Wairau River was estimated to be over 2,500 metres cubed per second, which swept away the main bridge on the west coast of New Zealand. The Milton Stop Bank on the true left hand side of the Wairau River downstream of the bridge was breached and major flooding occurred along the southern floodplain. I've been showing you a fly-through of some airborne LiDAR data that was acquired by James Brassington at Canterbury University that's been used to map channel change along the Wairau River. We can see erosion in red and deposition in blue. And this pre and post-event analysis can be used to identify overall zones of deposition, such as where we're just going through now, and areas of net erosion, for example, on the banks of the valley sides that we're just seeing on the left-hand side here. And then as we go up towards the glacier, again, very significant erosion of the valley sides providing sediment, and then lots of sediment being deposited here immediately downstream of the glacier front. So sediment budgeting in this case can help to identify, by disaggregating a sediment budget, zones of erosion and zones of deposition, and understanding where sediment is being supplied from during very large flood events. Sediment budgets might also be used to set research agendas and monitoring strategies. This diagram is from some river restoration scheme monitoring work that I've conducted in Scotland on the Outlaughy catchment, a catchment where a formerly straightened river was restored to let the river do the work, so embankments were removed and the river was allowed to re-meander and find its course across its valley bottom naturally. However, a monitoring strategy was put in place to monitor those elevation changes through time. In this diagram on the screen, you can see how a single meander bend evolved and how compound bars developed through time. We acquired a series of topographic surveys in 2012, in 2014 and 2016, and we've continued this research as part of an adaptive management strategy. Sediment budgets might also be useful in order to optimise dredging and nourishment strategies. And here are some images of gravel mining across, in this case, the Philippines. Monitoring river bed levels might help to inform sustainable strategies to ensure that consequences of gravel mining don't result in heightened geomorphological or flood risk. Equally, sediment budgeting can be used to assess the consequences of human interventions. In this example of the Bislak River, flood walls have been installed on both sides of the active river belt. Medium to long-term monitoring might determine whether the gravel levels in this reach are increasing or decreasing, potentially as a consequence of the hard engineering that's been imposed on this reach. Sediment budgets can also be used to improve numerical models. In the animation on the left-hand side of this slide, we can see a hydrodynamic model with water flowing from the top right-hand corner downstream to the bottom left-hand corner. On the right-hand side, we can see a sediment transport model and the results of that sediment transport model in terms of predictions of morphological change that occur during this high flow event, with erosion shown in red and deposition shown in blue. In order to calibrate and verify morphodynamic models like this, sediment budgets can be used to compare model predictions in terms of their patterns of topographic change and their overall sediment budgets to predictions. So I've focused upon a few of these arguments that have been identified by Frings and Ohl to calculate sediment and budgets.